Today we're going to be talking about how to use gradient vectors to find the maximum rate of change of the function at the given point. And in this particular problem, we've been given the function f of xy is equal to sine of x times y, and the point at which we've been asked to find the maximum rate of change is the point 1, 0. Now in a problem like this, the first thing we need to do is find the equation of the gradient vector, and then once we've found the gradient vector, we'll use it to find maximum rate of change. The reason we do it in that order is because maximum rate of change is always going to occur in the direction of the gradient vector. So if we have the gradient vector first, it'll make it easier for us to find maximum rate of change. So in order to find the gradient vector first, the first thing we're going to do is find the partial derivatives of f with respect to x and y. So for this problem, the partial derivative of f with respect to x, here we're going to take the partial derivative of sine of x times y. We're going to treat y as a constant when we take the partial derivative with respect to x. So given that, we have to use chain rule. We're going to treat sine as our outside function and x times y as our inside function. So the derivative of sine is cosine. That's the outside function first. So we take the derivative of the outside function, leaving the inside function completely untouched. But then we have to multiply by the derivative of the inside function. Well, the derivative of xy, when x is our variable and y is the constant, is just y. And remember, you can think about that as if you were taking the derivative of 3x, for example, and you had this constant 3 multiplied by the x, the derivative of this would be 3. You'd only be left with the constant. Well, in this case, we have x times a constant, y is our constant, so we're only going to be left with the constant y. So we go ahead and multiply this by y. And what that leaves us with for our partial derivative with respect to x is just y cosine of the quantity x times y. Now we're going to do the same thing to find the partial derivative of f with respect to y. We'll take the partial derivative of f with respect to y. We'll take the derivative of the outside function first, leaving the inside function completely untouched. So again, we'll get cosine of xy when we take the derivative of our outside function. But then we have to multiply by the derivative of our inside function. And in this particular case, we have the opposite situation where we treat y as the variable and x as the constant. So we multiply by x, and we're just left with x times cosine of the quantity x times y. Now the partial derivatives are effectively giving us our gradient vector. When we write the gradient vector, we write it like this. We say the gradient vector of f of x, y is going to be equal to, and here we just take our partial derivative with respect to x, so we get y times cosine of x, y, comma, the partial derivative with respect to y, which is going to be x times cosine of x times y. So essentially, we just called our gradient vector the partial derivative of f with respect to x, and then the partial derivative of f with respect to y. This equation for the gradient vector will allow us to find the gradient vector at any point for this function here, sine of xy. So this is a general expression for the gradient vector no matter where we want to find it. In this particular problem, though, we've been asked to find the gradient vector at the point 1, 0. So we're going to say the gradient vector of f at the point 1, 0. And we're just going to plug the point 1, 0 into each of our partial derivatives. So when we do that, we can go ahead and do that directly in this equation for the gradient vector. We'll plug in 0 here for y, so we'll get 0 times cosine of 1 times 0, comma, x is 1, so we get 1 times cosine of 1 times 0. And now at this point, we can just simplify. So we say the gradient vector of f at the point 1, 0 is going to be equal to 0 times this cosine value here. Obviously, it's just going to give us 0, so we get 0 there. And here we have 1 times cosine of 1 times 0. So in other words, cosine of 0, which is just 1. So our gradient vector then here is the vector 0, 1. Now that we have this equation, we actually know two things. Not only do we know that this is the equation of the gradient vector at the specific point 1, 0, we also know that the function increases fastest in the direction of this gradient vector. In other words, it increases fastest in the direction 0, 1. And now that we know its direction, it'll be easy for us to find maximum rate of change. So maximum rate of change is going to be denoted like this. We're going to say the absolute value of the gradient vector of f, and we could find a general formula for this, but let's go ahead and find maximum rate of change of the gradient vector at the specific point 1, 0. So we'll say the gradient vector of f at 1, 0 is going to be equal to, and now here's your formula. All we're going to do now that we have our gradient vector, all that we're going to do is take each of the values in this gradient vector here, 0 and 1, we're going to put them underneath a square root sign, and we're going to square both of them and take the sum. So in other words, we're just going to take our first value here, 0, and square it. And then we're going to add to that the second value here, 1, and we're going to square that, and we put it all underneath the square root sign. And then we say that f of 1, 0 is equal to, here obviously we just get 0, 1 squared is 1, the square root of 1 is just 1. So what this tells us is that our final answer is that the maximum rate of change is equal to 1, and that maximum rate of change occurs in the direction of the gradient vector, which is the vector 0, 1.